Hey everyone, welcome to the nerve center of clean energy in Oakland. First of all, I want to say a big thank you to Kachi and the Sungevity IT team for making this happen. Thanks very much. And also thank you for SF Scala. Thank you all of you for coming out to see us. It's appreciated. So let's just kick this off. Yeah, really? Okay, cool. So the first question I typically get asked when I do a phone screen is, you write Scala, is it for the panels? And the simple answer is kinda yes, sort of no. So what do we do here? Well, we write software. We're just wrapping up a major second iteration of our customer experience application. We're very proud of building probably one of, I don't know, maybe less than a dozen Siren hypermedia APIs. We're very keen on the HTS concept. So we've built out a pretty sophisticated API that sort of exposes our rich domain model. We also do cool stuff with monitoring. So we're actually monitoring customers' PV systems and kind of aggregating information. So there's a definite on-ramp for us there in the future for things like Arca and particularly Spark. So what do we do? One of the big things that we built out with our API and also our client applications is we actually handle interactive quoting for PV systems. So it's a big deal for us to explain the value proposition of what solar is in terms of, here are the financial options for the various kind of products that we offer, and here is the environmental payback. It's very important for us to also be a trust-based business, so we use our Scala software to really build a relationship with our customers over the lifetime that they have PV systems. The thing that we're really excited about that we're going to move on to next is our next generation of design tooling. So we're looking at where Scala fits in for very large-scale automation of designing PV systems using rooftop imagery. So this is our stack right now. We're big into type-safe products. We use Play, we use Slick, a lot of Scala test. We're also moving into reactive Mongo, and of course we use SBT. For the future, we're looking at Arca and Spark and figuring out how we can do how we can move into the big data space with all the data we're starting to collect. So I'm going to hand you over to Luke Smith, who's going to talk about functional domain modeling and our experiences with it. So thank you all for coming and enjoying this growing company.
Thank you. Yes. So I'm going to talk about how we do functional domain modeling here at Sungevity. And the subtitle is Beyond Buzzword Compliance, because my objective is to explain that we aren't simply putting the word functional in front of domain modeling. What is functional domain modeling? It's making functional code correspond to real meaning in a language that programmers share with other people, including other people in the company and customers. Why would we do this? Well, Sungevity needs to tell a very simple story, but a true story, to each customer about their specific interaction with a very complicated problem, which is getting solar on their roof. Customers don't need or want to know about the complexity of the various jurisdictions, the funding products, the taxes, utilities, funding providers, all the kinds of things that they don't need to know or care about. So we want to tell, for every customer, the simple story of solar for universal need, or SFUN. And that's only the first bad acronym I'm going to introduce in this talk. But basically, the simple story of our business is Sungevity looks at your home, designs a system, estimates how much that system will cost and how much electricity it's going to produce, and then shows you the resulting savings. And then we put it on your roof and we give you access to that installation's performance and design information over time. Telling the simple story successfully and reliably at scale means rigorously accounting for a lot of complexity through domain modeling. It's an idea that's commonly associated with traditional stateful object-oriented environments, but not tied to them. it's fully compatible with and maybe even more suited to functional approaches in using Scala. But how is that? Well, my assertion is that actually functional domain modeling is the original domain modeling. The word domain comes from modeling semantic domains. In linguistic parlance, a semantic domain is a set of concepts that are grouped by having something in common. So like the real set of music notes, types of snow, pizza toppings, etc. And in computer science, in reference to programs, a semantic domain is a mathematical object for rigorously assigning meaning to programs using denotational semantics, relating the program to the actual set of real objects. And it's compositional. It does so by figuring out what the various parts of the program mean and how they're composed, and then figuring out what that means. Dana Scott, along with someone named Strakey, was working on this in the 70s, and it's a pretty old concept. Lambda calculus at the time didn't have a mathematical model relating it to functions. So when he was writing denotations for programs, he then needed to create a model for relating those lambda calculus denotations to semantic domains. So Scott domains are more restricted than just sets, and they provide a general semantic model for computable recursive programs, but in most cases we don't have to worry about that, and we can think of the domain as a simple set, and that's true in this talk too. So long story short, Scala and Lisp, adopted syntax similar to these semantic denotations on purpose, and I think that I can assert that functional domain modeling is the OG domain modeling. It's useful because it builds up compositional denotations, and it's very compatible with functionalism because in fact it has functional origins. So even if you're not really interested in building up formal mathematical proofs, it's still a good way to communicate about your code base and its real structure. So I'm going to talk about a toy version of the Sungevity domain called utility consumption sites. Why not just houses? Well, because the thing on the left is a utility consumption site, probably, but the thing on the right is not. So Sungevity is mostly interested in places where we can offset someone's utility consumption by putting a system on their roof. And we don't sell off-the-grid systems yet, so utility consumption sites. So back to the story of Spun, this value proposition, this core product that Sungevity provides, we can identify components of it that are semantic domains, sets of real-world objects. So giving them names, Sungevity looks at your utility consumption site, creates a system design, calculates the system price, and your production estimate, gives you a quote that shows your savings. Once the system is built, we provide access to your installation, showing the system design, utility consumption site information, and now your utility consumption site is also a solar production site that provides some kind of monitoring access. And arranging these according to their sort of logical overlap, if we just consider utility consumption sites, well, a subset of those are utility consumption sites for which we have designed systems at any given time. A subset of those are priced. A subset of them also have production estimates. Some of them are priced and estimated. And then once you've got pricing and estimation, you can have savings, right? And the journey from A to B is essentially giving someone a quote. For the purposes of this talk, the operations are really simple, but assume that these are things happening on different systems over different periods of time, could be expensive calculations, et cetera. And finally, C to D is the journey from quote to installation, where we add the solar production site. So we can imagine, we're building an API with some routes that are going to carry us across these state transitions in these overlapping sets. So we can visualize this a different way, which is as a grammar of the domains. And we can think about which products of those domains that we're interested in. So installation is a product of the solar production site, the utility consumption site, and the system design. The quote is a product of everything except solar production site. And then finally, what's at the top? What actually describes the entire story? Well, I've called it the SPUNIT. Sorry, we love that acronym here. Anyway, another way of fully labeling this graph as products is like this. And these, to emphasize, these are the real world sets, right? The set of all possible utility consumption sites and the set of all possible system designs is a domain. So we can also imagine it as a state machine where we're trying to move through these states. And as you can see, we have some options, right? And this shows that there's an opportunity for parallelism in at least some of these operations. And if we imagine this as a play app where we're defining routes, we can actually say, well, those transitions, the movement through this model, can be defined by routes, like so. And so when you post a system design to some existing utility consumption site, we carry it through adding the system design, composing it, pricing and estimating, composing the results of those calculations, then calculating savings, and finally arriving at quote. So this is a state machine that performs a rough denotation of what the route would do. Same here with posting a solar production site to move from quote to installation. So installation doesn't include everything in quote, so we're actually forgetting stuff here. And you could look at this as a moment where we actually achieved the SPUNIT, right? We actually achieved the maximal production, and we could log it or something. But in this model, I've just said, well, no, we're going straight to installation. But the point is, we've now, at this point, traversed a path that includes every element. So how would we actually implement these kinds of things? Well, how is it a guide to actually writing code? Finally, there's some Scala on the screen. Well, if we define primitives like a utility consumption site about someone's address, their usage information, and their utility price, and then a system design as being this domain, which is just the product of those primitive domains, right? We can also define all of the other objects, all the other sets, as Scala code. And some of them are traits and some of them are concrete, just to make them composable. But basically, each one of these base ones is one of the things at the bottom of the grammar. And then we get to something like this, which seems ridiculous, priced and estimated utility consumption site trait. But you can see that as it extends system design trait with system price with production estimate, we can place it in a very sensible place in our hierarchy of productions and say, well, this is the thing that we get right before we calculate savings. This is the input to the savings operation, which presumably might be really expensive or something. We might have to do that asynchronously. So if we would name other products of this grammar, and we could say price and estimated system would be one of those. And you could label any vertex here. So the quote then ends up being the thing that extends the priced and estimated thing, utility consumption site, with the savings. And now we get a big value that is the product set of all the others. Same here with installation, extending the utility consumption site, the system design, and the solar production. And crucially, I included this to show that we can leave things behind. We can forget about the savings at this point, and still, we don't require it. Because we might not want to impose that restriction on ourselves in every situation. If it's installed, even if we don't want to generate or price a quote anymore, we can still do this. So those were the models that are accumulating the traits, but services need to provide them and move the state machine through the expensive transitions. So looking at production estimation service, this would be a function from system designs to production estimates. And crucially, this service needs to know nothing about anything it doesn't care about, including utility consumption sites. And this is a very simple operation just for the demo purposes, but essentially, imagine this was really hard, really a complex transition. Similarly, we have a pricing service where you can provide a function into a future of system price from system design. And similarly, when we're doing that savings calculation, we can include all of those traits that we defined as necessary for the quote, or priced estimated utility consumption site to savings. So looking at why this pays off. When we're doing the application of a system design, say someone has, outside of the API, completed the design, we can compose all of these transitions into a for comprehension or whatever, so it's a reactive stream flow, anything, that successfully carries the state machine through the transition. And here you can see the utility consumption sites getting found, the pricing service is making a call, the production estimation service is making a call, and the results are being composed. Those two calls could complete in any order. And then finally, after they have, the savings calculation can be made, and we compose the savings onto the price and estimated site into the quote. And that corresponds to movement through this kind of a state machine. And we can say that our code has a direct, a more or less direct denotation with functions between actual domains. How does this kind of thing look? Well, we use Siren, which I won't explain completely, but basically it's a JSON structure that can describe its class. And it can describe more than one class. So once you get back your full quote, it can show you that it's a member of all of those domain sets. And it defines all of the properties that any one of them requires. So similarly, when we post a solar production site to make an installation, we can do a very simple comprehension and say all we really have to do here is compose, find the quote and compose it with the installation, and we know that we have a fully valid installation. So this is the moment where we actually knew all of the elements of this unit. Oops. And here's the result. This Siren entity is saying, I'm a member of the domain installation, I'm a member of the system design. I'm also a utility consumption site and a solar production site, and I have all of the values associated with it. So, mission accomplished. We've done a loose semantics of our code, and we know what the different parts of it mean. And these denotations provide an anchor point between code and meaning, a function from code to semantic domains, basically. The program and its programmers can communicate completely and correctly with humans about representations about how its representations are composed. And we have a pretty good positive proof, in quotation marks, that it is correct for the whole domain, not just for tests on specific inputs. And there's a whole lot of caveats here. How do we persist this? Don't we need to, model events, think about streaming? I could explain a lot more about how we serialize with Siren and how we deal with containment. And it shouldn't be mistaken for real mathematical proof of rigorous denotational semantics. For one thing, we haven't explained the semantics of Scala or concurrent programs. But I think it offers a higher degree of certainty than we might otherwise have about the program's meaning and a way to communicate about it in real language. So that's it. The slides will be online somewhere. And here's some links that I found useful. And you can follow me on Twitter if you're interested. I swear I didn't make up my username just for this talk. Anyway, thanks very much. Oh. And now let me introduce my colleague, Suresh.
Hi, everyone. I'm Suresh Prakasam, Senior Software Engineer at Sungevity. Anybody has experience with the Play framework? Can you raise hands? Oh, so many of them. Okay. So when I started with the Sungevity, like I've seen, we have a API platform project. It's a big API. It will turn out to be a big API platform project. So I saw that there is a potentially it can turn out to be a complex, large applications. So I explored the options of creating services, a kind of sub-modules inside the big Play API platform. Then I find a very useful feature in Play framework. It's creating sub-modules. So I have created a small demo. So the contents are going to be, I'll explain the background and the folder structure, and there are a couple of demos. So why the submodules? So as I said before, we want to introduce reusable, modular, separately deployable services, and the submodule supports modularity. You can separate the modules by functionality. And then you can also create a Play module or as well as the non-Play module. So if you enable the Play Scala plugin, or if you are using Play Java plugin, it will become, eventually it will become a Play module. Otherwise, it's a non-Play module. So the scenario for non-Play module is you may have utility methods, or you want to separate out your business logic, which is not at all related to your Play application, basically. So we are using Play as a REST API layer. So you can move all those logic into a non-Play module, and package them, deploy them, reuse them as a library. So the next point is reusability. So multiple Play applications. It offers multiple Play applications inside the one big root Play applications. So this is the typical Play app folder structure, as you know. So the root app has controller, model view, MVC. We have a conf folder. If you see, there is a folder called modules. So Play supports submodules. You need to create your modules under the modules folder. So going. So this is the demo I've told you before. So the root application have an app folder, and it has a commons. The commons is a non-Play module. So I didn't enable the Play Scala plugin. And if you look at my build SPT, which is in the root folder, so I have two Play modules, module A and module B. I have a commons, so which is not a Play module. So I have enabled plugin, Scala plugin, Play Scala plugin for module A and module B. And my root project depends on module A and module B. Sometimes you don't want your root project to depend on modules, submodules. So I have two modules. And the major part of the Play framework is the conf file, and your routes file. The routes file has your API endpoints. So these are all the endpoints I have in the root app, and I have configured two other routes file. So Play will route the endpoints which are not available in this file to the corresponding modules, module A routes or module B routes. And if you look at the conf file of the module A, so I have included the root application conf file. Sometimes you may need the configurations from the root app. So submodules may need to access the configuration from your root app. This is how you do that. And I have a router, so in case if I package and deploy the module A separately, this router tells the Play to where to route the endpoints. This is the model A routes. So I'm switching to the browser. I'm going to start the Play app. It's already started. So I got the response. I hit the endpoint / index. I'm using Postman as a REST API client. So I'm the root application. So I'm going to hit the endpoint, which is in the model A. Sorry. So I'm the model A. I got the response. I'm the model A application. So this is going to the model A routes. If I package and deploy the model A separately, this should still work. I'm going to show that. So before showing that, so model B, it says model B application. So if you see, I have an endpoint to read the configuration from the application configuration file. So there is only one configuration in the application.conf of the root play app. And I have one configuration in the model A application.conf file. I'm also reading the configuration from the root play app. So we have two key value pairs here. So I'm going to now package the application. So here you can see SPT packages modules separately. So we have a module A, module B, and the root app. So let's see the module A. So the play application from module A is up and running now. I stopped the play application from the root application. So going back to the browser, you can now see, so module A is packaged and it's running separately. So you can only see the configuration from the module A. So it's not reading the configuration from the root app. Let's check the other endpoints. Yep. And going back to the IDE, I have one more endpoint, which is actually using the implementation from the commons module, which is a non-play module. So I have a method implementation. It's just a util method. It is used by the controller in the module A. Yeah, you can see that here. So now module A is up and running separately. Let's go back to the browser. So I'm going to hit the endpoint which access the commons module, which is a non-play module. So you can see I'm splitting the URL into protocol, domain, and top-level domain. So going back to the slides, we have seen some demos, how the folder structures are organized, and what are the benefits of submodules. So realistically, we may package and deploy the services separately or reuse them as a library non-play module. So there are lots of benefits. The one more thing, you can have a clear separation between your modules. So I have a test in the module A. So if I run this test with the coverage, it's going to show me the coverage only for module A classes. So creating submodules in Play framework really helps us to maintain modularity overall and the reusability. Thank you guys. Any questions?